Hi, hello, and today's lecture is going to be the start of our infinite impulse response filter design and how we actually go about doing these design processes in particular. So we basically discussed before that any digital filter design can be based off of some analog version, and there was a relationship between the Z domain and the S domain, where we can see here from lecture 11 that Z was basically equal to the exponent to the power of ST. In order to start doing infinite impulse response filter designs or IIR filter designs, we're going to have to start thinking about how we can use the S-plane filter and substitute for S accordingly. And we're going to be exploring this in particular in this lecture. So, IIR digital filters are basically used when linear phase is not important, and we start with some analog prototype. And we convert that into a digital design by doing analog to digital mapping or spectral transformation to achieve the desired frequency response. We also need to pay attention to the aliasing effect, so that way that the sample frequency must be at least that or twice that of the filter bandwidth. Otherwise, we're going to get the aliasing effect. And in general, we start to use like 4 times that of really good results when we're doing IIR filter designs. So the design approach requires that we choose some analog prototype. So it can be any one of these filters here, a Butterworth, a Chebyshev, a Bessel. And then we approximate the behavior of the analog prototype in one of 2 ways. We either match the time response, which is basically giving us the impulse invariant design, or we match the frequency response, which is using the bilinear transform. And we are required to know how to do both of these designs. So we need to know how to do the impulse invariant design, and we also need to know how to do the bilinear transform accordingly for any IIR digital filter. So basically, we start matching the digital filter response. We start matching the digital filter response to any analog prototype response for a given input. And in this case, we typically use an impulse. And the response for any impulse, when we think about it, is that an impulse contains all frequencies, so we subject any system or filter to all frequencies to obtain the frequency response of the filter. The transfer function obtained typically gives us a good match for that signal, and it may not match for another input. For example, if we decide to use a step or a ramp, we may get an entirely different response altogether. So typically we start with x of t here, which is going to be the input signal in continuous time, and we sample it to get x of n. We then transform it to get into x of z. At the same time, we also have x of t here. We transform it into get x of s. We apply it into our system equation because we need to know how will we get the output here. H of s is going to be the system or the filter that we already have or we already know. And then we do the inverse transform to get y of t. And then we sample that to get y of n. We can also transform this to get that into y of z. Once we have x of z and y of z, we basically are able to find h of z given by this equation here. So let's actually look at this process in an example. So we're starting off here with h of s equal to 1 divided by s plus 1, and we need to convert this into a digital filter h of z. And we're going to be using the impulse invariant design technique, and once we have this design technique, we would have to assume a sampling time or a sampling frequency. Typically it's given to you. If it's not given to you, assume one and just use it throughout the entire design. So the first step is that we need to figure out what is x of s. And basically, since we're using x of t as an impulse, we check the Laplace table. The Laplace table for impulse and time is just going to be 1 in the s domain. Because you also know that y of s is equal to h of s by x of s, and x of s here is going to be 1, that means y of s is basically just going to be h of s, as seen here. We then do the inverse transform, so the inverse Laplace transform in particular, to get y of t. Once we have y of t here, and we had our sampling time being t of s is equal to 1, we can transform y of t here into y of n. And once we have y of n, we can use the z transform table to get this into the form as required for y of z. Because we knew that x of t here was an impulse, if we check the z transform table, for impulse, x of z is just going to be 1. So now that we have x of z and y of z here, the last question to ask is what is h of z? Which is basically y of z divided by x of z. And we get the final equation here. At this point, the impulse invariant design technique tends to be finished, because that's the only thing that we need, the filter in terms of z. What this spectrum looks like, on the other hand, and you're not really required to do this, this is for observation purposes, is that we transform from h of z into h of capital omega, and we plot with respect to omega. And this basically gives the idea like what's going to be the frequency response and the phase response accordingly. So, the magnitude response, as you can see here, this basically gives you an idea, okay, this is going to be the magnitude here for the frequency response and the phase response. And this is for h of s. So the blue line here represents the magnitude response, the green line here represents the phase response. And this is regards to h of s. But when we move into h of z on the other hand, this happens, where we can see that the entire behavior changes accordingly. And whereas the magnitude response tends to be almost the same, the phase response has changed entirely. And this is because when we did this transform, the phase moves from a linear phase to a non-linear phase accordingly here. And the reason why it goes non-linear is due to the approximate behavior of moving between the transforms. So in commenting on this, this means that we need h of s to be expressed in some form so that we can get the inverse Laplace transform. And typically we use partial fractions to achieve this. And once we have a partial fraction solution that can be transformed back into the time domain, this basically gives us the idea that the design is going to be stable because the analog prototype here is stable. And if you recall the S-plane to Z mappings, that means everything on the left-hand side of the S-plane indicates that the system is stable, and the Z-plane, everything inside the unit circle indicates that the system is stable as well. The final thing we need to make sure is that the sampling frequency and the filter bandwidth must be noticed such that it applies to the Nyquist frequency or the Shannon's frequency theorem. So that means that the sampling frequency must be at least twice that of the filter's bandwidth to avoid any aliasing. The amplitudes, on the other hand, tend to have a scaling factor. In this particular case, there was a 1.6 amplitude factor. So if you watch here in particular, the analog prototype given by the red line was centered around like the 1 magnitude here. And then the digital one given by the blue line here is giving you an idea that it was closer to 1.6. So this is, it represents the physical scaling from 1 to 1.6 here accordingly. The scale version basically is if we move the original here and we try to match it back to the same amplitude accordingly. The scale version could also refer to as a normalized version. So let's think about how can we represent this in some sort of block diagram if we had a h of z. So h of z here in this case is given by this equation, and we need to figure out what's going to be the input-output difference equation. So h of z basically maps to y of z divided by x of z, and then we could do equation mapping accordingly, and we get back this in terms of y of n and x of n accordingly. Once we have it in terms of y of n and x of n, we can then just map the inputs and outputs accordingly to get back to our block diagram. So IIR Digital Filters tend to both have feed-forward and feedback paths because we tend to have recursive solutions and we tend to be reliant on feedback, meaning that we need to have some feed-forward path for feedback to occur. They can be represented in cascade and parallel forms, depending on the type of design, but we tend to leave in the canonical form in particular. So let's watch our second example here. We're going to be converting this h of s equation here to h of z using the same impulse invariant design technique, and we're also given a sampling time equal here to 0.5 seconds. So h of s here can be broken down into partial fractions as seen in this gray block, and then we can do the inverse Laplace transform to get it back into h of t. We then transform it back into h of n, and then we could transform h of n to h of z accordingly, and we could get this associated transform here. If we don't want it in negative powers of z, as we can see here, we can delay the entire property accordingly by multiplying by z on the numerator and z on the denominator, and we can transform it into positive powers of z here. Once we have h of z here, we basically recall the standard form of h of z in this form here, and we can just cross multiply it accordingly to get back into the standard form. We also need to substitute this sampling time here equal to 0.5, so t of s is 0.5, and then we just cross multiply accordingly and we get back in terms of the standard form h of z here. So once we have it in standard form here, this tends to be our final answer for the impulse invariant design technique. If we decide to plot this, which is not required, but we just observe the behavior, we can see the magnitude response is basically going to be somewhat similar to what we had from before, but the phase response has the non-linearity because of the approximation factor. If we compare the impulse responses, we can see here that for h of t, we tend to have some initial high value, and then we approach some steady state value as we keep on going. H of nt still has the same sort of behavior because there's just a sample form here. If we decide to block diagram that standard form h of z equation that we saw in the previous slide, it will look like this. And typically, like I said, any block diagrams that you have for IIR filter designs, we tend to represent them in canonical form. So this brings us to the end of the first IIR filter design lecture.